Hi again, Mike with Robert at the project site. In my last video, I talked about the building of this foundation pad. Today I want to talk about factors of safety in the design and construction in relation to your house or building structure. I'll tie this discussion to the Champlain Tower South building collapse and an iconic building structure that was built 139 years ago, the Brooklyn Bridge. So let's get started. The design along with the construction of this pad and the concrete foundation is about 3 times the required load, so it has a factor of safety of 3. Stated again, this foundation has 3 times the required strength needed to withstand the weight of the structure and not fail in the foundation. In the building of this foundation pad, we achieved a soil-bearing pressure of around 3,000 pounds per square inch by excavating out 3 foot of unsuitable soil and replacing it with 4 foot of select structural fill material. We will also construct a post-tension slab to transfer the building load across the building pad, to which the building weight could be upwards of 400,000 pounds. Why did our structural engineer include this factor of safety of 3 in his design? Because there may be some construction inefficiencies during the construction of the building pad and the concrete foundation that may hinder this design's overall strength and durability. Items like missing reinforcing steel in the slab, inadequate slab thickness, improper backfilling procedures used in the building of the pad, and not excavating to the required depth to remove the unsuitable soil. You eliminate these deficiencies by inspecting the work during the placement of the foundation. You check the proper depth of excavation, the proper select fill material, and the placing of the fill material, and then inspecting the concrete foundation before and during the concrete pour. I'll give you an excellent example of the factor of safety used in designing and constructing a significant structure, the Brooklyn Bridge. I'm going to tie this discussion of factors of safety of the Brooklyn Bridge to the Champlain Tower South building collapse in Surfside, Florida in June of 2021. The Brooklyn Bridge took 14 years to build, from 1869 to 1883. It was the longest steel suspension bridge globally, as it spanned from Brooklyn to Lower Manhattan over the East River. The total span was near 1 mile. John Roebling designed the bridge, and his son Washington Roebling constructed it. One of the main points in the design and construction of this bridge is John Roebling's factor of safety, which he set at 6. The design and construction would be 6 times as strong to hold the intended weight. John Roebling was born in Germany in 1806 and was educated there as a bridge engineer. By the age of 24 in 1831, he immigrated to the United States with an entourage of German farmers and settled in the town of Saxonburg, Pennsylvania, just north of Pittsburgh. He began farming, but before long, Roebling grew bored of farming and began surveying for the Pennsylvania Railroad. He surveyed across the Allegheny Mountains in western Pennsylvania through the town of Johnstown. Near Johnstown, at the Portage Railroad, there was a system of long inclined planes designed to haul canal boats up and over the Allegheny Mountains, between Hollidaysburg at the foot of the eastern slope and Johnstown at the foot of the western slope. 9-inch diameter hemp rope that was over 1 mile long was used to haul the boats up over the mountains. But they wore out and in short order would snap in two, sending their loads crashing down the mountainside. John Roebling saw that he could make a rope with 1-inch thick iron strands of wire. These were laid up first, then twisted into a larger rope by a hand machine. His wire rope was accepted by the railroad and used, as it was stronger and more durable than the hemp rope. With his new invention, John went back into the bridge design and construction business. He used these iron ropes as the suspension hangers in the design of his suspension bridges. He designed and built his first suspension cable aqueduct bridge over the Allegheny River in nearby Pittsburgh. In 1846, he designed and built the Monongahela River Suspension Bridge in Pittsburgh. From 1851 to 1855, he designed and built the Niagara Falls Suspension Bridge, and from 1856 to 1867, he designed and built the Cincinnati, Ohio River Suspension Bridge. And in 1869, John presented his preliminary design of the suspension bridge to the New York Bridge Authority. But the Bridge Authority was concerned over the safety of his cable suspension bridge. You see, in the 1860s and 1870s, 40 bridges a year fell, about one in every four built. In the 1880s, 200 bridges fell. They mainly were railroad bridges that failed and cost the most lives. The bridge in Ashtabula, Ohio, failed in 1877 and killed 92 people. It was built of an iron truss design, and it was only 11 years old. Because of these recent bridge failures, John presented his preliminary design of the bridge to 9 bridge board members and 7 civil engineering consultants. The consultants were John's idea, so that his plans would be subjected to careful scrutiny by a board of experts. In their considered professional opinion, his bridge was perfectly possible. All were sound, practical builders, an eminent body of civil engineers. John's plan was for the bridge to be held up between 2 towers by 4 immense cables, 2 outer ones and 2 near the middle of the bridge floor. The bridge would measure 5,862 feet and weigh 18,700 tons. The cables would be 15 inches in diameter with vertical wire rope suspenders as thick as pick handles. The cables were steel, the metal of the future, not iron wire that had been previously used on suspension bridges. His critics stated that a single span was impossible and that the bridge trains would shake the bridge structure to pieces. They discussed the Wheeling Bridge, destroyed by heavy winds in 1854. Well, John relieved their concern by stating that the bridge floor needed weight so that it would not oscillate in the wind like the Wheeling Bridge. His iron truss design, with a combination of triangles at the trolley area, would also give the bridge rigidity and stability, unlike the Wheeling Bridge, which did not have this design. The truss design would be 12 foot high to run the entire length of the suspended floor. The inclined stays would have a total strength of 15,000 tons, enough to hold up the floor by themselves if the 4 cables were to fail. The New York Bridge Authority and the 7 civil engineering consultants approved John's design after visiting his recent bridge projects in Pittsburgh, Cincinnati, and Niagara Falls. Tragically, John died right at the start of the bridge construction by getting his foot crushed by a barge boat while surveying the East River. His son, Washington, took over as the chief engineer of the bridge, and in January of 1870, work commenced at the site. The Brooklyn and New York towers were completed by 1875, and in 1876, the New York Bridge Authority bid out the steel wire rope for the project. The New York Bridge Authority member received a bribe from a local wire cable supplier from Brooklyn for the award of the wire contract. Now, Washington Roebling had inspectors at this nefarious contractor's warehouse during the construction of his wire cable. They would perform stress tests on his assembled wire, and if it failed the test, then it was rejected. Wire that passed the stress tests would be stamped approved. Now, this supplier would take the approved, accepted wire cable in his wagons and transport it to another warehouse. He would then switch out the approved wire cable for the inferior rejected wire cable and transport it to the bridge. The workers would then install this inadequate rejected wire cable. It was a Bessemer steel wire, and it was about 85% the strength of the approved crucible steel wire. Roebling's inspectors did not catch this deception for about 2 months. During this time, they installed 221 tons of this defective wire cable in the bridge structure. The original specifications had a safety factor of 6 for any possible imperfections in the manufacture of these wire cables. Due to this defective wire, Washington then calculated that the overall factor of safety for the bridge was now at 5 instead of the original design of 6. Therefore, Washington deemed the bridge safe. Despite these setbacks, in October of 1878, the last wire cable was installed across the bridge. The decks commenced, and in 1883, the bridge construction was completed. 37,000 people a day were using the bridge, and in 5 years, 30 million passengers a year were using the trolley trains. They inspect the bridge every 2 years. There have been 15 times that they have performed repairs on the bridge. And from 1944 to 1954, they strengthened the trusses and installed new horizontal stay cables between the 4 main cables. And since 2008 through this year, they will spend $750 million to refurbish and reconstruct the entire Brooklyn Bridge. Now let's go to the Champlain Tower South building and the tragic collapse that happened last June 24th, 2021, in which it killed 98 people. I reviewed a couple of YouTube structural reviewers, most notably Josh Porter from Building Integrity, who extensively analyzed this collapse. He discusses that the central area of concern is the pool deck area and the planter box area. According to Josh, in his review of the structural drawings, the structural engineer had inadequate beam support for the planters. The beam support was for a 1-foot step down into the pool area, and in Josh's review of the structural engineer revised his drawings on January 17, 1980 to show no structural beam under the planter area. You see the 21.5 inch by 12 inch beam under the planters that were eliminated. And when they eliminated the beam, they eliminated the support under the planters. Like Josh says, these planters are very heavy with concrete, block, dirt, and plants. And here looking at the cross section. In his calculations for the pool deck area, he determined that the factor of safety was 1, meaning they designed it for the exact weight that it would hold and leaving no room for error in either the design or during the construction of the building. You see here where the planter boxes fell and precipitated the collapse. It's because the pool deck slab connects to the east side of the building. If you look at the structural drawings, you'll see a small shear wall at the stairwell only on the east side of the building. Now, shear walls give structural rigidity and stability, bracing from wind or other moment forces in multiple directions, much like John Roebling's truss design on the bridge deck. And some structural analysts have determined that this east side is at a minimum design and construction. In this drawing from Mike Bell, you see the red structures are the shear walls. And on the west side of the building, the side that did not collapse, they had a lengthy shear wall at the elevator banks. And they had stout columns and transfer beams on the first floor, as you see here. That helps in any shear and moment forces inflicted upon the structure. As you look back at the east side structural drawings, there is no lengthy shear wall, nor are there any transfer beams between the columns, just straight up and down columns to tie to a flat slab. There is also a discussion among structural engineers of the lack of punching shear reinforcing steel at the column locations. Some structural engineers now suggest that the punching shear rebar would have strengthened the columns and would give some factor of safety in the building. Transfer beams would also increase the stability of the structure, as it did on the west side of the building, and then possibly adding another bank of elevators on the east side and encircling it with a shear wall from the ground level to the penthouse floor. In a typical concrete high-rise, you'll see an elevator bank in the center with a shear walls around them, and then they'll have stairwells at the ends of the floors with a structural shear wall around them, also up through the entire building. Then that gives it stability in every direction. For this Champlain Tower South building, Nathan Reber, who was the developer, he oversaw the entire project from the financing to the land acquisition and the design and construction. He's the only person that reviewed the structural engineer's design, and I don't believe that he questioned the structural design, nor did he inquire of the factor of safety in the design. In John Roebling's Brooklyn Bridge design, he had 7 civil engineering consultants review it. Now, for sure, when you have a higher safety factor in your design and construction, you are paying extra money. And as Josh Porter states, the pool deck area had a safety factor of 1. There is no leeway for any deficiencies during construction in items like missing reinforcing steel or the inadequate spacing of the rebar or the insufficient design under the planters, and so on. And as Josh states, incredibly, the Champlain Tower stood for as long as it did with a factor of safety of 1 at the pool deck. As we know, Mortabito engineers performed the 40-year recertification as required by Miami-Dade County. Their review was for a physical review of the structure, and they provided a written report indicating the necessary repairs for the building. They had no responsibility by law to investigate the factor of safety for the structure or areas of the structure like the pool deck area and the support of the planter boxes. We know that in response to this collapse, the Florida Congress has passed Senate Bill 1702, which now states that every multifamily building that is 3 stories or more must have a milestone inspection performed. Within 3 miles of the coastline, the inspection must be performed at the 20-year mark and then inspected every 7 years thereafter. All other multifamily buildings not within this 3-mile zone would require an inspection at the 30-year mark and then inspected every 10 years thereafter. And within the bill, they provide a definition of what milestone inspection means. It's just an structural inspection of the building by a licensed architect or engineer authorized to practice in the state for the purposes of attesting the life safety and adequacy of the structural components of the building, and to the extent reasonably possible, determining the general structural condition of the building as it affects the safety of such building. As I've highlighted, the purpose of such inspection is not to determine if the condition of an existing building is in compliance with the Florida Building Code. Inspection teams are not required to review the structural design of a building to ensure that it has a reasonable factor of safety, nor are they required to review the lack of support for areas such as the pool deck area at the planter boxes. If they would have been required by law, they may have found that the structure was designed and built with a low factor of safety. It then would be imminent for the owners to provide temporary support and immediately commence the reconstruction and maintenance, especially under the planters. You may be in the design stage of your upcoming building project, and you should be curious about your structural engineer's factor of safety in his design. If it's a low factor of safety, perhaps you could inquire about the cost of increasing it by adding more beams and columns or shear walls. I'll discuss in my following video how value engineers can help an owner assess their structural building factor of safety and give recommendations if necessary. And I wish you success on your upcoming projects. Thank you.
Success. Success. Success.